Welcome, algebra students, to lesson 8.1, first lesson in our new book on linear functions, and it begins on page 2. Now, it goes through page 15, and that's because there are just a lot of illustrations on these pages. But let's get right down to notes. Most of this chapter is notes, so let's get going. So first of all, vocabulary. In linear functions, the word function is important. A function is where a variable y is a function of another variable, let's say x, if for each x there is exactly one value of y, which is determined by x. Okay, now that sounds like a lot of gobbledygook, and it is, but it basically is illustrated in this illustration. So here you have an input-output thing. Anything that goes into the hopper, you apply the same rule to, which is the function, which is like a 20% discount. So if you put 50 into the hopper at 20% discount, it comes out with exactly one y, which is 40. If you put in x at 100, it comes out at 80, which is the y. And if you put 150 in, there's just one answer, and that's also here 120. So you apply the 20% discount to these numbers, and there's, for every input, there's one output. So 50, 40, 100, 80, 150, 120. So basically, that's what all of these words mean, is this. So a function can be represented in a variety of ways. You can represent it in a table of values where for every x there's a y, and we've done that already. And then you can take those table of values, the x's and y's, and put them into ordered pairs. Then you can take those ordered pairs and put them on a graph. Or the fourth way is you can take all of that and determine an equation. So moving right along, we're going to go to try it number 1, and that would be on page 4. So, page 5, page 5. So in try it number 1, we are directed according as it reads, the initial depth of some water in a barrette is, and I have no idea what a barrette is at all. Maybe it's a beret. Don't have a clue. But anyway, the initial depth of some water in that thing is 24 centimeters. Can't be very big, whatever it is. The water level decreases by 4 centimeters per minute. Let y centimeters be the depth of the water after x minutes. So in A, they say copy and complete the following table. So they have the x's, which are minutes, and they start off initially with 0 minutes, and that would be, the start would be 24 centimeters. And then they go up by 2's. Now remember, every minute is 1. So every 2 minutes, or every minute is 4 rather, and every 2 minutes therefore is 8. So it says it decreases by 4 centimeters per minute. Therefore, it's going to decrease by 8 centimeters every 2 minutes. So it's just going to go down by 8s as we go along every 2 minutes. And so 24 minus 8 is 16, 16 minus 8 is 8, and 8 minus 8 is 0. So that's how we filled in the chart from the information given. Then letter B says, draw the graph of y against x for 0 is less than or equal to x, which is less or equal to 6. Okay, so minutes, the units would go this way, and we went through 6. I went a little further. On your graph, you're going to be using the graphs that have the blocks of 5. Always use the ones that have the blocks of 5 because you can get more precise. On my notes here, I had to be a little more sketchy. The depth, we're going to go up by 5s, 5, 10, 15, 20, and so on, because we have a 24 here, so that's almost 25. So I chose to plot 0, 24. So 0, and I'm almost to 25 up here. And then I chose to plot the next one on 0, so that would be 6, 0. And then I just connected my dots. So minutes that way, depth that way. I labeled it out. I called it minutes and depth, and so on and so forth. Then letter C says express y as a function of x. That means write an equation, basically. So the function y is where you begin, and that y is going to equal 24 centimeters minus 4x, because you're always multiplying the minute by 4s, and you're starting with 4, and you're going to subtract some multiple of 4 from it. So y equals 24 minus 4x, and you can kind of see how that works. So we'll put 24 minus 4 times 0 is 24. Here you go, 24 minus 4 times 2 is 16. 24 minus 4 times 4 is 8. 24 minus 4 times 6 is 0. So that's your proof of that function. Okay, this probably is the most challenging to get in the order that they gave you, but it all is in the wording of the problem too. Now, moving on to linear functions. It's the next topic. Here are the notes. Let me see if this is all in here. It is. So linear functions, when you graph a linear function, the graph is always going to be a straight line. And the form is always y equals mx plus b, where m and b are the constants. This involves slope. It's the slope formula also. Remember that slope, recall from last year, slope measures the steepness of a line. Slope is the rise over the run, which is the vertical change over the horizontal change. The y-intercept is the point of intersection of the linear graph with the y-axis, so the vertical axis, wherever the line goes across, that's your y-intercept. Therefore, y equals mx plus b is a straight line. M would be the slope of your line. It's always some form of a fraction, so it's like 3 over 2, like change over the rise over the run. Or if it's a whole number, remember 3 can be written as 3 over 1. So no matter what the number, the slope will be some sort of a fraction. And then b will be the y-intercept. Wherever it intercepts at the y-axis, that is what b is. So it's the point of intersection at the y-axis. Another thing to keep in mind is the rate of change. Rate of change are ratios to compare rates at which two quantities change. And another thing, the y-intercept is the initial value where the value of y corresponds with x equaling 0. So we noticed that on our first graph that we did where it was 24, 0. So that would be your initial value, your start value. So with all of those things in mind, and that actually makes a little more sense as you work with it, we are going to go on to example number 2, not example, but try it number 2, which is way on page 12. So here we go. Oh, there's one more thing to write down before we do try it 2, and that's linear modeling. When you model a line or linear modeling, you use linear functions to describe or approximate relationships in the real world. So you take something in the real world and you put it on a graph. Okay, so now we can do try it 2 on page 12, which reads, the table shows the distance y kilometers traveled while driving in the city. And then they go ahead and show you hours, so 1.5, 2, 3, and 4, and then with the corresponding distances in kilometers is 75, 100, 150, 200. So the first thing is draw a graph of y against x for 0 being less than or equal to x, and which is less than or equal to 4. So again, this time I labeled it over here. The time or the hours are 1, 2, 3, 4, 5. The distance, I went up by 50s, and then I started plotting 1.5, 75, and then I went 2, 100, then I went 3, 150, and then I went 4 and 200. So all those little X's are my ordered pairs. And then I connected them, and then I extended this line down to 0. So in this case, my y-intercept is also 0, because you're not taking any time to travel 0 kilometers, so it kind of makes sense. Then I connected them, and I kind of did my rise run thing, in which when you make a rise and a run at a right angle between 2 points. So between these 2 points, the rise needs to go here and over, and between these 2 points, it will go up and over. These 2 points, it would be very tiny. It would be boom, boom. So the rise and run goes between 2 of the points that you have plotted from your ordered pairs that fit the function. So B says find the slope of the graph and explain what the slope represents. So again, slope is the rise and the run. To find the slope, pick any 2 points on the line or within a table. And in this case, I'd use the table because it's always easier to see the points on a table. And then you would take your y values and you would multiply, or you would subtract the second from the first in each case, and the x's are in the denominator position. Again, the second from the first, or this way. So I chose the 2 points in order that they appear, 2 and 100 and 4 and 200. So I start with my y's and go 200 minus 100, and then my x's 4 minus 2. So when doing that, it's 100 over 2. 100 divided by 2 is 50. Okay, so it's 50. And what does that slope represent? I don't think I answered that. The slope in this case would represent 50 kilometers per hour. So that would be the rate of speed, 50 kilometers per hour. Yeah, sorry I didn't mention that. Now moving on to C. Here we go. It says find the initial value of y. Well, by extending that line, let me go flip back. That's why I needed to extend the line back down here. So the initial value of y is going to be 0, because at rest, you've gone nowhere. At 0 miles per hour, you're going nowhere. So y is equal to 0. And then the function, therefore, is y equals 50x. And that would be determined from what we just did. Going on, we're going to try another one, try it 3, which is on page 14. Try it 3 reads, there's a small crack in a water container and water is leaking from it. The graph below, they drew the graph, that's nice. The graph below shows the amount of water, y liters, that remained in the container after X hours. So if you look at that graph, 12 is the y-intercept. So initially at 0, when it starts off at 0 time passing, it had the full 12 liters in it. And then over the course of hours, it leaked where it ends up with where it is at 5. Okay, so A says, find the rate of change of this relationship. What does this rate show? So first of all, you got to write down what you're seeing. It's always good to just put it down on paper. So from the graph, at the beginning, there was 12 liters in the water container, and that point is 0:12. After 5 minutes, there was 9 liters in the container, and that point is 5:09. And you get that from the graph. So A says the rate of change. Well, I'm going to take my 2 points, and I'm going to minus the y's. 12 minus 9 over the x's, 0 minus 5. Now notice that's going to be negative. So 12 minus 9 is 3, 0 minus 5 is negative 5. It's a negative 3/5. I change that into tenths. It's a negative 0.6. Okay, so what does this rate show? It shows negative 0.6 liters per hour. That means, because it's negative, this shows that every hour 0.6 liters of water leaves the container. Because really, you can't have a negative amount. But what that means is this. So this is what it shows. And this would be the answer to A. This shows that every hour 0.6 liters of water leaves the container. That answers what does this rate show. Because this is the rate, but in the negative part means it leaves the container. Okay, the next one. B, what is the meaning of the value 12 on the vertical axis? Well, it just means 12 is the initial amount of water in the container. That's pretty straightforward. And then C, how much water remained in the container after 24 hours? Well, after 24 hours, we started with 12, and we're going to subtract the rate, 0.6 times 24, which is, again, a negative 2.4. So after 24 hours, there's no water left because you're already below what is even able to be there. So that's how you answer those questions. Okay, that is your lesson. Read, rewind, pause, rewatch as often as you need to. I will give you your assignment in class. You will need the graph paper. If you don't have a supply, go and help yourself from the container that is behind Noah James and Alexa. You will find graph paper there, and I will give you your assignment in class. Okay, thank you. Do good math.